So welcome to the software testing track. And our first speaker today will be Jim Woodcock from the University of York, Professor of Software Engineering. So Jim is Professor of Software Engineering in the Department of Computer Science at the University of York, with research interests in verification of computer-based systems. He's a member of York's RoboStar research group, one of the largest research groups in the world in software engineering of robotics. So with that, I'll hand it over to Jim. And yep, sorry about being confined with the mic. But...
Okay, well, thank you for the introduction, and thanks also for the invitation to come and speak here. It's a really interesting event. I've already spoken to a lot of people from companies and from industry and made a lot of contacts, so I was really pleased to be here. So I'm going to talk about two projects in York, RoboCalc and RoboSim, which are both projects in this RoboStar program. And I'll talk specifically about RoboChart and RoboSim, which are two notations. It's joint work with our electronics department, but also with people in China. Okay, so we're back in business. Okay, so when we started our work a few years ago, we did some investigation of current practice in industry and the development from scratch of robot controllers and their hardware platforms. And the current approach is kind of summarized by this diagram. If people have an abstract model of their robotic system at all, it's always a state machine, nothing else. It's the only game in town. And from that state machine, they might develop a simulation, and simulation is the only verification technique, simulation and testing, the only verification technique that we found widely used amongst industrial practitioners. And in that simulation, the controller code will be derived from the abstract specification, if at all. There'll be a simulation of the desired hardware, and some discretization of the environment will be simulated. And then from there, using a code generator in every instance, something like C++ will be generated as the deployed code in some real robotic hardware that somehow corresponds to the simulated hardware and a particular continuous environment that is approximated by the discrete environment. Now, if during the simulation or during the testing of the deployed robot, mistakes are found in the design of the robot, we didn't find a single example where people would go back to the model at the top, the abstract model, and change the state machine. In quite a few cases, they went back to the simulation, but the majority of uses are at the deployed level, so they'll change the C++ code. So this is about as far away as you can get from model-based engineering. So here's an example of a state machine. This is a state machine for a swarm of robots, well, a shoal of underwater robots. And it's a problem of searching the seabed for something, or perhaps looking at metal fatigue in chains for oil rigs. You have a robotic submarine that goes down, makes some checks, finds something interesting, and needs to report it to a surface vessel. Now, you can't use radio waves underwater, so blue light signaling is the technique here. So there's a protocol for keeping the whole shoal of robots at just the right 20 centimeter distance to make that signaling possible, perhaps in a rough sea. So here's a description of the controller, a rather illegible description as far as I can see, but if you look at it a little bit, you can see that there's a state that's shared between two state machines. There are inter-level transitions that are breaking the hierarchy and so on. It's not a formalized state machine. So even when state machines are used, they're not used in a way that you can attack them for verification with any formality. So here's our approach that we're pursuing in this project with our industrial partners. And so we're starting from a model here of the environment and the controller and the hardware platform. And this is a diagrammatic model that's, I hope, attractive to practicing engineers. And from that, we automatically generate a proof object, a piece of mathematics that doesn't need to be seen by the robotic engineer at all, but is the input to some automatic verification tools, model checkers and theorem provers. And I'll talk about those later. Up here are some properties of interest interests that should be satisfied by this robot when it's deployed. And those are put into these verification engines, and perhaps the verification fails. And so we'll go around this loop until it's valid, until it passes. And at that point, we'll automatically generate a simulation model in RoboSim, another diagrammatic language I'll talk about. And that then goes into a robotics simulator with some test cases derived from the model. And again, there's now a loop here and here, where we carry on these test cases, hoping that they succeed. And when they don't, we go back and we change the model, generate the mathematics, go through the verification, come back to the testing. And eventually, we'll pass out here and generate automatically the deployed code. And then there's some system testing of the real robot and its actual controller, with test cases that have been converted from the ones that we've used. And again, there's a loop here, going all the way back round. So if these tests fail, we go back round and we change the model. We generate the proof object. We go back through the simulation and so on. And eventually, what will come out of here will be a robot that's certified for safe use. Another one of our projects is called Sci-Fi Assure, which is about going through the certification process and gathering the sort of evidence that regulators need for this kind of thing. And for here, it's going to be the code for the controller, the evidence from proofs and test results, the assumptions that were made about the environment, and the restrictions that are then needed for the environment. So that's our approach. Thank you, my lovely assistant. So RoboChart then is a domain-specific modeling language specifically for use by roboticists, not by academics such as me. It's based on UML, but it's restricted. It only has some of the diagrams. It has state machines and component models, and the physical robot is explicitly modeled. It's also enriched with timing properties and probabilistic choices. I'll talk more about those a little later. There's a simplified compositional semantics and automated reason that makes it suitable for very automatic uses of model checking and quite automatic uses of theorem proving. The semantics is a mathematical model familiar to some of us here, process algebra. And there's a tool, a plug-in for Eclipse called RoboTool, where you can construct your model and check well-formedness and do the proofs and so on. So here's a schematic for the tool. For RoboTool, we start with requirements, and we have some RoboChart models that correspond to those requirements. And then there are three paths through this diagram. The top path goes from the tool with the mathematical object into the model checker FDR4 and the theorem prover called Isabelle Hull. And out of that, you get qualitative results. The second path is here with reactive modules. And then we use some existing probabilistic and statistical model checkers like Prism and Storm. And from that, we get both qualitative and quantitative results. Like, for example, how much battery power does this need to cover an arena of a particular size? That kind of quantitative result. And then down at the bottom, we can generate languages like C++ for use in existing. And out of that, you get results in the keyboard. Ah, well, oh, there you go. Almost okay. So RoboChart models identify a particular robotic system, a single robotic platform. If you want swarms, then you'll have several of these modules. And the interaction with the robotic platform is through shared variables and operations and events. You can have one or more controllers. Sometimes it's nice to structure a controller as a collection of parallel controllers, and sometimes you have a distributed collection of controllers. And I'll say a bit more about communication in a moment. So the controller models a specific behavior and contains those things I talked about, where the state machines describe behavior. Communication between controllers is synchronous, and between the controller and the hardware is asynchronous, because that's how the hardware works. State machines themselves are self-contained. There's a well-defined action language that we can analyze. There are no interlevel transitions. There are urgent transitions. There are timed primitives where you can describe time passing using clocks, delays using weights, and you can have deadlines over events and actions. And then there are probabilistic choices. So you can have a probabilistic control algorithm, perhaps for estimating the current pose or something using a ransack algorithm. And then you can reason about how many iterations do I need, and therefore what the real-time behavior is going to be in order to get a particular probabilistic guarantee that I'll have no outliers in my observations. And so you can then put that probability to use in putting restrictions on the kind of hardware sensors you've got and how reliable they have to be. Second language, the one for simulation. There are many commercial simulators like NetLogo and Argos and Enki and so on, and Simulink and Stateflow. And in all these cases, the simulation is a cyclic executive, right? And that's not the structure of a RoboChart. The structure of a RoboChart is a diagram that captures the behavior. It's not specifically about this cyclic executive. So RoboChart is based on interrupts with events being handled when they become available. There's no notion of that cycle. So we want a diagrammatic notation for simulation and to be able to relate the abstract specification in the state machine to that simulation. So here's how the RoboSim works. On the right, there is a state machine describing the simulation. On the left, not very legible, I'm afraid, is the executive cycle I've been talking about. An infinite loop where in the first part, we collect information from registers, then we execute some actions and operations, and then we write back to the registers, and then there's a wait, and then we go back round again. And these two things together are in parallel, the executive driving the state machine as though it were a piece of sheet music, right? Doing what should be said in a particular order. Here we have buffered parallelism, and the visible behavior here is about those register transfers, what it's reading and what it's writing. In the RoboChart, it's not, it's about events. So there's a discrepancy in the levels of abstraction there that needs to be bridged with the refinement technique. So what's a correct simulation? That, after all, is the talk that I promised to give was about what a correct simulation was. The criterion is that every behavior of the simulation is permitted by the RoboChart abstract specification. So every behavior you see was permitted. You can't see a behavior that wasn't permitted. So there's no test you could carry out on it if we verified it. There's no test you could carry out where you would see something that wasn't permitted. Everything is correct. That's the criterion. So at the abstract level, it's about a sequence of interactions, traces of events, but also refusals to interact. So we might say, during this time period, the robot must not do the following. So as well as positive things happen, it's these negative things that mustn't happen. Right, so both a sequence of interactions and refusals to interact, and deadlock and live lock and time properties and so on. Down at the RoboSim level, it's about reads and writes to global variables. It's about operation calls. Thank you. Okay, so what's the correct simulation? Here's the summary of that. RoboChart is describing order, availability, that's the refusal or not to do things, about time of access to global variables and events and operation calls in the platform. RoboSim is describing order and availability and time of the register transfers in a cycle. And we need to relate those two things together. So we need to say when a particular register, say read, goes true, but that corresponds abstractly to detecting an obstacle, to the event about that. And perhaps writing to the writes variable corresponds to a call to the move operation. And we need to link those things up, and that's the kind of retrieve relation, as it's called in informal. And change that interrupt-driven view to a cyclic view. So that's what a correct simulation is all about. So we compare RoboChart and its assumptions to the RoboSim model. And the RoboChart, we can calculate from it a mathematical object. Nobody needs to see that except for us. You can calculate that mathematical object with the assumptions that we need to make this work, because the robot is not going to work without assumptions. We make assumptions about the environment it will work in. About the connection of input events to register read events, about the connection of object calls and output events to the register write events, about events not occurring between cycles, about cycles having at most one occurrence of each output, and in each cycle, each operation being called only at most once. And so we make that connection. And then what can we discover from that? Well, the mistakes we can find, we can't write a simulation for this machine. it misses the weight that's important to understand the length of the cycle. Schedulability is about finding the common denominator, the least common denominator of the cycle times for all the things that we need to simulate. We can't implement this as a simulation because it misses an entry action. We can find that fully automatically. This has 2 moves in a single step. This one misses an abstract event, so something hasn't been implemented. This one misses the treatment of one of those abstract events obstacle. So the event has been implemented, but not in the way that the abstract event has been described. Here, we're actually ignoring an abstract event. So here, not doing something is significant, and we can detect that. So that's where we're at. We've got this way of describing robots and their controllers and their hardware platforms and their environments. At the 3 levels of abstraction I talked about, at the very abstract view, that's the RoboChart, at the simulation view, and then at the deployed level, with formal links between them so you can do formal and automatic proofs as you go down. We've got a couple of case studies I wanted to mention. A driverless pod, of course, an autonomous vehicle is always going to be a good example. But we've got a local sandwich maker that uses robots in making sandwiches. It's really, really important business to the local area. So we've been looking at how we can generalize what they do. And there are some interesting correctness and hygiene and therefore safety requirements that need to be followed here. So those are our examples. In the future, well, there's lots of things that we're ignoring here about computer vision. We have crude ways of describing computer vision using algorithms like ransack and so on, but it's not a very sophisticated way of doing that. I'd like to be able to prove things about learning algorithms, about them being safe and so on, and about human-robot interaction, and about ethics, and about safety cases and so on. So what we're doing really is applying what we've learned over many, many years, in my case the last 40 years, about the theory of software engineering here to robotic engineering and producing robots that we can assure and that we can trust. And if you generalize this one step further, what we're talking about is actually the theory of cyber physical systems. Thank you, Michael. I'll stop there.
Thank you, Jim.
Thank you very much.